All right, let me hit this first announcement while I'm remembering to do it. I've announced it before, but I want to keep encouraging you. The math team, their name of the prime examples, are beginning their practice session for next fall's competitions, but we found out this year we need to start earlier than a few weeks before the competition. So Friday at 12 noon, every Friday in C100 on the Birmingham West campus, Mr. Racy, who's the coach, will be meeting with students then. They've also planned another time Mondays at 3. So if either one of those work for you, both of them C100 on the Birmingham West campus, or if you want to have practices out here anytime during my office hours will be fine, as long as we'll talk about that a little bit too. So anyway, wanted to get that done. Still trying to, I guess finally it's open. So let's go from current slide here, and then we'll, but before we get to this, sorry about last week and a half. It's been a while. 2 Thursdays ago, I told you about this. They scheduled me to start a new drug, and they were going to do a 10% dose on Thursday to make sure I could handle, because sometimes people have pretty severe reactions to it. Went no problem. Okay, so then the next day, Friday, I had the 90% dose, and that no problem, went just fine. By the time Monday rolled around, I was pretty exhausted, okay? I could tell something was happening. My wife says it's all in my brain, but I really felt like there was a battle going on inside. But I drugged myself in for my 9:30 class on Monday and stayed till my 2 o'clock class and then drug home. And I mean, literally, it was that bad. Everybody who saw me said, well, you look better than you did last week, which is damning with faint praise. But anyway, but then Tuesday morning, got up, showered, ate breakfast, dressed and everything. I sat down on the sofa and said, I can't drive. I mean, I was that totally exhausted. So that's when I started sending the things. And I went upstairs, went back to bed. I don't sleep in the daytime. I slept till noon. I mean, solid almost, just unbelievable. So I thought I could get up and come down, get in for the afternoon session that I was going to use to make up for Thursday. No. I tried, could not make it. So I was just totally exhausted. That's when I sent the second one. Okay, I know you're in here. There you are, Lindsay. All right. Now, Wednesday I drugged back in and taught those 2 classes again like I had before. Remind me of your name? Huh? Yeah. Gavin, right. Okay. But Thursday morning I woke up exhausted again. I said, I'm going in. I'm going to make it in. But I was running late because everything was just really dragging. Got in the car, got to, I don't know if y'all know where Red Mountain Expressway merges into 2059. Dead standstill. So I was just able to get off and try to make my way through downtown Birmingham to try to get on further down. First couple of places I went, roads were closed. So the next place I went was only going the other way, not south and west, but north and east. So I kept going, finally crossed under the expressway, but there's no entrance on that street. I said, I give up. I'm just going to drive surface roads and get here whenever I can. Well, everybody else was off the expressway too, so it was just jam-packed everywhere. And I got here about 8:20. Of course, most of you had already gone. And I saw the list. So what I did, okay, is it Brianna? Yeah, I thought so. So I went on and started class, started the recording, and decided that just wasn't going to be any way we could make up all three of the classes before. So I found the three classes on last year's that sort of mirrored what we had been doing now. They're not an exact fit, but pretty close. And I announced this, so if you go and you watch the YouTube videos, I show you which classes to choose from. I apologize about YouTube video because when you're just in the screen mode, you hear my voice in the background because it's doing the recording. I mean, so you'll hear me talking, but that's in the background too. Hopefully you can figure out which is which. So anyway, you're going to have to make up those three classes that way, and then Thursday's class, it's in two parts. I think by the time I got the system up and running, and by the way, one student did show up. He came in late, so he got the class to himself. So I got about, 30, 45 minutes of it done, but then I had my trig class coming up, so I taught my trig class, and then I went back and did another Math 112 class. So I did it for about another 45 minutes or so. So there are those out there too. Now they're at the bottom, and just to let you know how it is in YouTube, they always put the new recordings at the bottom. So those two are at the very bottom. The three that you'll need to make up, they're near the top. Not at the top, but near the top. Same sections, I mean, so if you'll follow that. So I did get everything finished of 1.6, and we're starting 1.7 today. Sorry about this thing, and I'm still, let me explain to you why I was so exhausted. Well, I'm being treated for, it's a chronic lymphocytic leukemia, so my lymphocytes are way high, So they were at 100, my white cells were at 128,600. The normal range is 7,000 to 11,000. I was at 128,000 plus. That was before the treatment started, that first treatment on Thursday, 10%. Well, when I went to have the treatment last Friday, they said, yeah, you'll do blood work, so we'll see if it's being effective, but we're going to give you the second treatment anyway. So I was in the middle of having the treatment when the blood work finally came back, 1.1 thousand. So it had dropped from 128,000 to just over 1,000, which is way below the range it should have been. I don't think I should have gotten the treatment last time, but I think it surprised everybody at how effective it was. Chris is here, right? Okay. And so that was part of what was going on. The second part of it is that it also affected my red blood cells. They've been low because the white blood cells being so high suppresses the red. So my red blood cells, hematocrits, and hemoglobin have been low. This knocked them even lower. So that's why I was totally fatigued last week. And still am. Yesterday I didn't come in until 9-ish, 8:45, 9 o'clock. And I hadn't planned to stay as long as I did, but I wound up staying a full day. I'm not sure I'll stay a full day today either. To Darius, but I can't find you. There you are. Okay. All right. So, I may not be here during all my office hours this afternoon. Just depends on how the day goes. Part of the problem with having now low white blood cells, and especially neutrophils, which are some of the white blood cells, my immune system is almost zero right now. And this is one of the worst flu seasons we've had in close to a decade. Okay, so, and then my wife being epidemiologist, she reminds me of all the other viruses out there that could put me in the hospital as well. So she said, you lay low. So I say, yes, ma'am. So anyway, hopefully I'll make it through today's class, and I'm feeling less fatigued than last week. I started to say so much better than last week. It's too strong a word for it, but less fatigued than last week. So, Sorry, I shouldn't have taken that much time on that. Any questions on anything up till now? For those who just came in, I hope you're listening to the YouTube videos, because Chris and I were here for the first half last time, and so we got that recorded. He had a class, so he couldn't make it back for the second half, but both of those are out there, and I refer back to the ones in YouTube for that you need to do on your own. So we're starting 1.7. Any questions up till now? And again, for those who just came in, do not leave today without the quiz. Now, it just seems like when it rains, it pours, like it has this whole weekend. I left the quizzes and the graph paper to be copied yesterday afternoon. When I came in this morning, they were still in the box, and the copy person wasn't in the office. So I ran around, got a key, went in to make copies. I think I got 7 copies made or something like that, and the machine shut down. Actually, yesterday I tried to make the copies myself, but it had a warning light. I didn't know what to do with it, so I just left it in the box. I had plenty of time, I thought. And while I was in there trying to figure out how you're turning the machine off, turning it back on, all this kind of stuff, the lady came in who runs the copy room and said, nope, it's broken. I don't know how I got 7 copies made, but it did. So that's why I was sort of late getting up here, because I've been down there for at least 20 minutes trying to get the machine to work. But Miss Glass, fantastic Miss Glass, said, oh, how many do you need? And what she did, she scanned and then printed the remaining copies that I needed. So I hope I have enough. But I couldn't get the graph paper. I thought that was asking an awful lot of her to get the quiz. I've got some graph paper. I'll give out what I can. Any that I don't have, I'll get it to you some later time. Anyway, don't leave without the quiz. And if I can find enough copies of the graph paper today, do it. Any questions? All right. We're still in Chapter 1, Functions and Their Graphs. And in Section 1.7, your quiz covers 1.4, 1.5, and 1.6. 1.7 is transformations of functions. Okay? I'm sorry, my throat is really raw, sore, and my head is not as bad as it was this morning. I found out I cannot shake my head without it hurting, so I'm going to try to keep my head as still as possible. I never have headaches, so this is really a new experience for me. I mean, I have them occasionally, but nothing like this. All right, so the first thing we're going to do is use vertical and horizontal shifts to sketch the graphs of functions. Then we'll use reflections across the x-axis or y-axis to sketch graphs of functions, and we'll use non-rigid transformations. Vertical and horizontal shifts, the whole graph shifts up or down, right or left. Okay? Non-rigid transformations, they stretch or they shrink. They change their shape somewhat. Okay? You still have the basic shape, but it's either stretched or shrunk in some dimension. So this is basically what we'll be doing here. And so we're going to start with the shifting graphs. Okay, those old shifty graphs. Now, did anyone hear the 1.6 YouTube video? Did anyone listen to it? I know Chris was here. You need to listen to that, because that was talking about the parent functions, the shape of your basic graphs. Now, we've done most of those, and any that we haven't done, I think you'll see they're pretty simple to see and to understand, but if not, please ask. So here is many functions have graphs that are simple transformations of the parent graph. Now, what we did before in 1.6, this graph here, the gray one here, is f of x is equal to x squared. We call it a parent function. It's the simplest parabola you can have. Okay? The coefficient is 1, and of course the exponent is squared. This is called the squaring function, or is the name of the function, I guess you say, the simplest quadratic function you can have. That's one with the maximum exponent being 2. And it's also, the shape is a parabola. Okay, so this this function, h of x, which is x squared plus 2. Now notice that's f of x plus 2. So what have you done? Remind me, what is f of x? Y. Very good. That's the y value. Okay? If you add 2 to the y value, what do you do to it? You go up the y-axis by 2. And if you'll notice here, 0, 0 was on the parent function. Now 0, 2 is on this one. Go up 2. Okay? 1, 1 was on the parent function, and negative 1, 1 were on the parent function. You go up 2, and then 1, 3, negative 1, 3. So everything goes up 2. 2, 4 on the parent function. Negative 2, 4 on the parent function. Go up 2, and you have 2. You can't see it here, but that would be 2, 6. Continue this on up, and that would be 6. Everything goes up by 2. Okay? That's called a vertical shift. You're adding or subtracting from the parent function. Okay? By shifting the graph of f of x, x squared, up 2 units, as shown in this figure. If this had been a minus sign, this would have been shifted down 2 units. Okay? Or up 3, or down 5 halves, or whatever. It's just moving up or down the y-axis. Does that kind of make sense? Okay. In function notation, f, h of f, and I've already said this, are related. The h of x was x squared plus 2, but we said f of x was x squared, so that's f of x plus 2. Your y of your parent function shifted upward 2 units. Similarly, you can obtain the graph of, now here's a different kind. Before, you were adding or subtracting from the y, the f of x. In this function, g of x is x minus 2 in parentheses squared. What are you adding or subtracting from here? The x, not the y. So guess what this is going to be? A horizontal shift. Very good. Now, the last time they started with a plus here they're starting with the minus. Which direction you reckon this is going? You would think it would go left. Look where it's going. It's going right. Now, let me just say this. It's sort of a dumb way to do it, but I think if it has to do with the x, it's backwards. Okay? The y's go the direction you expect them to go. The x's don't. They go the opposite direction. Okay? So x minus 2 is going to shift to the right 2. And it kind of makes sense because if you put a 2 in here, x equal 2, you're at 0, where you were here. So sure enough, x minus 2 is going to shift 2 units to the right. Where do you think x plus 2 would go? 2 to the left. You're absolutely right. Stand up, sit down, 5, 5, 5. Okay. Now, how do you graph this? 0, 0, go right 2, 2, 0. 1, 1, go right 2, 3, 1. Negative 1, 1, go right 2, 1, 1. 2, 4, on your original graph here, your parent function is to the right 2 more, and that would have been 4, 4. They didn't show it here, but that would have been, that extends on up to here. Negative 2, 4, they didn't show that here. So right, negative 2, 4, go right 2, and you're at 0. Does that make sense? Shifting the graph right 2 units. Every point, point by point. These are real easy to graph, the parent function, and then the shift is just make sure every point that you do the line, shift it, the number that you need to shift, and you've got the new function. Does that make sense? All right. In this case, the functions f and g and f have the following relationship. The g of x is x minus 2 squared. Now remember, the f function was your squaring function. So what you're doing now is f of x minus 2. Tells the f function squared what's ever inside here, and that gives you exactly that. So you see the 2 is being subtracted from, because it sends it to the right, 2 units, the graph of alpha. So this summarizes what we were just saying, and hopefully it follows pretty reasonably. Let C be a positive number, okay? Think of C as positive, and then whatever the sign that you see here, that's giving you the direction it's going, okay? Vertical and horizontal shifts of the graph of y is equal to f of x are represented this way. A vertical shift, C units up, is going to be what? F of x plus C, okay? F of x plus C. Vertical shift C units down would be, C's being positive, f of x minus C. Horizontal shift C units to the right would be f of x minus C. Perfect, okay? And C units to the left would be f of x plus C. Absolutely. Way to go. Does that make sense? All right. Some graphs can be obtained from combinations of vertical and horizontal shifts. Of course, they make it a little more complicated. And we'll see that in example. I guess we should have already done one, because they sure haven't shown it yet. Let's see. Oh, here we go. Yeah, they're going to show it. Okay. Will be shown, demonstrated in example 1b. The vertical and horizontal shifts generate a family of functions, each with the same shape, but different location in the plane. Okay? All you're doing is shifting the graph. Shifty graphs, you know. So here's example 1. Use the graph of f of x is equal to x cubed. Does anyone know what that one looks like? If not, we'll graph it fairly quickly. So there will be our vertical. There will be our horizontal. Give me a few points. We're going to graph this one right here. F of x is equal to x cubed. Give me an x. 1. What would then be your y? 1. Okay, so 1, 1 is on the graph. Give me another x. Say again? 2. Okay, there's x equal 2. What would your y be? Say again? Okay, if you plug in 2 for x, 2 cubed is 8. I can't even get it on the scale. 1, 2, 3, 4, 5, 6, 7, 8. It's somewhere up there, okay? I'll just pretend it's somewhere up there somewhere, okay? Give me a few more points. -1. Okay, that's over here. What would be your y then? -1. So that would be down here at -1, okay? Give me another one. -2, and that would be, any idea? Way down here at -8. You left off the easiest one. Y'all are such hard workers. I'm way lazier than y'all are. Second? 0. And what would 0 be? 0. All right, we got them. So this is going to be a graph that looks something like, yuck, not like, I don't want you yet. Okay, let's start and do it like this, going up like this, and down like that. That's your parent function, your cubic function. That's what it looks like. Okay? Now, let's do G. You tell me what color you want G to be. Say again? Green? Red. Okay. Okay. Was that red or crimson? Never mind, we won't go into that. Okay. All right. Red. And that's going to be our G, so I'll circle it so you know which one. What you reckon G is going to look like compared to your F? Down 1, okay? As soon as you see that, that's your F function, x cubed, minus 1. Go down 1. So that means 0, 0 goes down to 0, -1. 1, 1 goes down to 1, 0, and negative 1, 1, negative 1, negative 1 goes down to negative 1, negative 2. Okay? Still can't get the upper or lower ones, certainly not the lower ones, but this is going to be something like this and something like that. The whole graph is shifted down by 1. Does that make sense? All right. What color you want B to be? Green. Okay. We'll go with green for the H function. Okay. Whoa, what's happening with H here? Okay, certainly up 1, just don't say yours, okay? And what else? Hey. Okay. Left, how many? 2, exactly. So you go back to your parent function, go left 2, up 1, okay? This one goes left 2, up 1, something like that. And this one goes left 2, whoops, I don't have enough spaces there. And let's see, left 2, 1, 2, and up 1 to right there. And 1, 2, 3. Yeah, we still don't have time enough to do it. So it will be something like that. Well, it's not asymptotic, but it's going up like that. See how that works? You had a double shift there, a vertical shift up and a horizontal shift to the left. That's what they were talking about, the B part being a combination. Now, that's of that parent function, execute. Any other parent function is going to do the same type of thing. Keeps the same shape. Now, mine may not look like it. This blue shape here, same as this shape here, same as this shape here. It's just where they're located. Okay? And by the way, we do call those rigid transformations because the shape stays the same. It's just where it's located on the graph changes. All right, that's my rendition of it. Let me erase all this. Any questions before I erase it? Okay. And let's see how they do it. All right. So relative to the graph of f of x equal x cubed, they showed theirs being a little flatter in the middle than I did. Okay. I guess they're right. Okay. Then when they did x cubed minus 1, that nearly dropped everything 1. Okay. Dropped every point, point by 1. Okay. So the same shape here is here, but a vertical shift downward, by 1 unit. Okay. Almost as nice as ours, right? Not quite. Okay. Okay, the next one, remember, anything having to do with the x's go backwards, okay? So since that's a plus, that means it's going left, not right, okay? But the y's go in the direction you expect, up 1, okay? So this is going to go left 2 and up 1. There's that point right there, and every other point does the same thing, left 2, up 1. Okay, wherever that was. Left 2, up 1. And this one over here, left 2, up 1, there it is. So every point you have on there has a combination, horizontal shift to the left, vertical shift upward. Any questions? Okay. If you haven't noticed it already, this book loves graphing. Okay, so get used to it. That's why I needed to have graph paper copied for you for your quiz. I have some copies. I hope it's going to be enough. Okay? So in example 1b, you obtain the same result when the vertical shift precedes the horizontal shift. So it doesn't really matter what order you do it, as long as you do both of them. Or when the horizontal shift precedes the vertical shift. Both shifts, they don't interfere with each other. All right. So let's move to reflecting graphs. Another common type of transformation is a reflection. Boy, Today this board's coming in really handy. It's holding me up here. Goodness gracious. For instance, if you consider the x-axis to be a mirror, then the graph of h of x, which is minus x squared, is exactly the opposite of h of x, or f of x equal x squared. So f of x equal x squared, it goes like this. There's your parent function, f of x equal x squared. When you negate everything, every point on this gets negated to below. Now 0 negates to 0. Okay, there's not much change there. 2, 4 goes to 2, negative 4. Don't see it there, but it does. 1, 1 goes to 1, negative 1. And negative 2, negative 4 goes, positive 4 goes to negative 2, negative 4. So that's also a rigid transformation. The shape is the same, it's just its orientation has changed. It's a reflection across the x-axis. Okay, does that make sense? So everything gets negated, which means it gets flipped downstairs. Now, let's go back to the one we did before, the one that sort of looked like that, the cubic function. Now these flip here, that flips up. So that would then have been a function that looks like that. So that's the advantage of being in class. You won't see that on screencast on YouTube video because it doesn't pick up my arm waving. Okay, make sense? All right. So here are the rules for this. Reflections in the coordinate axes. Reflections in the coordinate axes of the graph y is equal to f of x are represented as follows. Reflection in the x-axis is when you negate what your y was. So if your y's were positive, they become negative. If your y's were negative, they become positive. You negated everything. That's a reflection across the x-axis. Now, a reflection across the y-axis is when you negate the x, okay? So whatever, if x was going this way for f, it'll go this way for h, because you're going in the opposite direction, which sort of makes sense. That's the reflection in the y-axis. In reality, we don't do that as frequently as we do reflecting on x, but it can happen. So here's example 2. Okay? Now, I'm not even certain. I don't think they mentioned this as one of the earlier ones, but we really talked about them. If you go back and listen to the past videos, you'll see that we did talk about these to some extent. All of your even functions, when your exponents are even, they're going to look a lot like your parabola. The differences here, this is x to the 4th rather than x squared. The differences are near 0, they're flatter. See, your x squared would come up a lot more smoothly. This one's flatter here, but then once you get outside of plus or minus 1, they go up steeper. Okay? So they flatten out between minus 1 and 1, and they're steeper outside of minus 1 and 1. So that's these are actually called quartic functions, so you don't have to know that. This is x to the 4th. Now, we'll talk about this more in the future, but if your parent function is an even function, it's on the up and up, okay? Everything is positive there, unless, of course, you negate that. Whereas odd functions, like that cubic function we had before, it goes up and down, okay? The even functions only go up in both directions, unless you negate them, and then they go down in both directions. So there is your parent function. F of x is equal to x to the 4th power. My throat hurts. All right. Now, each of these two graphs are transformations of that graph. What do you think g of x would be in this case? Second? Okay. It's a shift up by 2, but something else happened first. You flipped it. So the g of x would then be minus f of x, that's the flip, plus 2. So that would be minus x fourth plus 2. You see that? The flip took the x to the fourth that was up this way, cupping upward, flipped it across the x-axis and flipped it downward, and then the vertical shift moves it up by 2. So it would be minus x fourth plus 2. Does that make sense? You see it? All right. What do you reckon happened on the B one here? Remember, your parent function was x to the fourth. Say again. Negative x to the fourth. That flipped it across the x-axis. But now you do x minus 3. So it's minus an x minus 3 to the fourth. So let me write this one down. Let me go back to my dark color. This one would be, the g of x would be minus x to the fourth plus 2, or minus f of x plus 2. This one, the flipping down would have been minus x to the fourth, but the horizontal shift, 3 to the right, would be, oh boy, where do I write that? I'll write it up here. This will be a minus x minus 3 fourth. Okay? The minus sign here flips it, but you shifted the whole thing over here. So you might think of this as a horizontal shift first, then flip it over. And that, to me, helps me to see it a little bit better. This one, I think of that as a flip first and then a vertical shift. It really doesn't matter. Both of them work well, but I like to think of that as doing the shift first and then flip. Whereas this one, I see it better as flipping first and then shifting up. But they both work. Okay? Which would be also the other way to express is minus f of x minus 3. Okay? It's flipping it, but also a horizontal shift 3 to the right. Okay? You in agreement with that? Let's see what they say. The graph of G is a reflection in the x-axis followed by an upward shift 2 units. That's why I said, so it'd be f of x is x to the fourth, so that would be a minus x to the fourth, well, yeah, plus 2. Okay? So flip first, go up 2. That's how I like to think of it. Okay? The second one, though, is a horizontal shift 3 units to the right, then you flip it. Okay? So that would be the x minus 3 to the fourth would be shifting right 3, but negating that flips it across the x-axis. Okay? So minus x minus 3 to the fourth power. Make sense? All right. Now, when sketching the graphs of functions involving square roots, now, again, if you didn't watch the videos, you might, let me just go over that. Remember, you must restrict the domain to exclude negative numbers inside the radical. Okay? So let me, since I'm guessing most of you didn't see the video in time, but I put it out there. But let's just do y or f of x is equal to the square root of x. Okay? Now, your x domains have to be positive numbers. Have to be positive numbers. You cannot take the square root or any even root of a negative number. They all have to be positive. So I didn't leave this part of the graph out here at all, because there your x's are negative. We're only going to take that side. Okay? Give me a few points. Can you take a square root of negative 1? Don't think so. 1? Is that what you said? And what would 1 be? Square root of 1 is 1. So there, 1, 1 is there. Give me another one. Give me an x. 4. I like it. Okay, 2, 3, 4. What would its value be? 2. Excellent. Another x. 9. Oh, y'all are you got it. Okay, that's 5, 6, 7, 8, 9. What would it? Excuse me. Say again. 3. Okay. And you always leave off the easy ones, don't you? What is 0? 0. Of course it is. Okay. There is your at least 4 points on your square root function. Okay. Now, what that turns out being is half of a sleeping parabola. Okay. Turn the parabola on its edge and take the top half of it. There's your square root function. Okay. Now, what happens to that if you negate that? Say that again. Okay, let me first give me a color. What's that, yellow? Not yellow. Orange, okay. Let's try to get that orange in there. Ah, yeah. Okay, and what's it going to look like? I'm sorry I didn't leave enough room here. We're doing this one right here. If you negate 0, you get 0. If you negate 1, you get 1. So it's the bottom half of that sleeping parabola. I didn't leave enough room to show it, but it's going to continue on like this, right? Okay, that's exactly it. But what's the domain? You still have to have whatever is inside the radical, that's your x, has to be greater than or equal to 0, meaning non-negative. Because you can't take the square root of a negative number. It's CJ. Okay. All right. Now, what about the h of x? What color you want that to be? Give me a color. Red? Is that what I heard? Huh? Yes. Oh, okay. I can't hear well. Okay. Okay, red. So h of x is going to be this one. Now what you say is what's inside the radical. That's where you always go. If this is an even root, you don't see an index there, you understand it to be 2. So negative x has to be greater than or equal to 0, right? What's inside the radical, negative x, has to be greater than or equal to 0. Because you can't take the square root of a negative number. Okay? So the negative x has to be greater than or equal to 0. How do we figure out what x is? You remember the rules for negating directional... Say again? You say go to the right. What do you mean by that? Okay. Looks like to me this one is going to the right. This one and that one. But what happens here, if you multiply or divide, okay, let's start with this. If you add or subtract any number, positive or negative, to a directional inequality, that would be less than or equal to, greater than or greater than or equal to. Any of those directional derivatives, add or subtract the same thing to both sides, you don't change a thing. The direction stays just like it was. But when you multiply or divide a positive number by that, they stay exactly like they are. But when you multiply or divide by a negative number, you flip the sign, flip the direction. So that would then be x has to be less than or equal to 0. Because if negative x is greater than or equal to 0, it means positive x has to be less than or equal to 0. That's how they got this. Okay? From there. So what did that do? Your f function was the square root of x. What we have done with h is negate the x, which means flip across the y-axis, right? So what was a 1 here? Well, you change the 0, it stays 0. I mean, flip it. 1, 1 becomes a negative 1, 1. A 4, 2 becomes a negative 4, 2. And I almost hit this. I can't hit that thing because it'll turn it off. Okay, so that's going to be 3. Okay, whoa, that's not looking very pretty. Make fun of my drawings here. Okay, I got it. I'm not hurt by it at all. Okay. Okay, so you reflect it across the y-axis when you negate the x. You went from this to that. You reflect across the y-axis. How about k here? What color do we want k to be? I don't know if she wants to be a color, but what color you want her to be?
Blue.
Blue, okay. All right. Light or dark?
You pick.
Anyone have a choice?
Dark.
Dark. Okay, we'll go with dark. Okay. Yeah. Okay. On this one, here is, okay. That's a negative, the square root of x plus 2. Now, the first thing we have to do is worry about our domain. So how do we do that? We know what's inside the radical, which is what? X plus 2 has to be greater than or equal to 0. It cannot be negative. You cannot take the square root of a negative number. So you take what's inside the radical, x plus 2, and say it's greater than or equal to 0. Now, how can you solve that inequality for x? Say again? Subtract 2 from both sides, just like you did for an equality. And that gives us x is greater than or equal, because adding or subtracting doesn't change the direction. Only multiplying or dividing, and that's only if it's a negative number. Okay? Is greater than or equal to negative 2. So that's where they got that from. Okay? So we're in agreement now. And remember, your graph's going right through the minus sign. So what's going to go on here? This is a horizontal shift to the left 2. And what does this do? Reflect across the x-axis. Okay? So what we're going to do here, this 0, 0 here goes left 2 to be a negative 2, 0. Okay, that's where it's going to start. Then what happens? This plus 1 here is going to shift 2 this way, this way, but then go flip across the x-axis, so it's going like this. So, sorry I didn't leave enough room, but it's going to be just like this one was, negative square root of x, only it's going to be shifted to this way. So it's going to be, if you imagine the top half there, this is the bottom half of that parameter. Does that make sense? Sorry I didn't leave enough room down there. Let's see if there's left enough room. I think I can just flip to the new page. Oh, they didn't show it. Shame on them. Okay. This was example 3, while they didn't list it as example 3. But if you'll look in your book, and again, people at home can't see this, but look in your book here. The first one, you just negated it. You did the bottom half of that parabola. That was the orange. Okay? The next one, the red here, you negated the x, and that puts you on the other side, okay, of the y-axis. And then the third one, you had a negation and a shift, or a shift and then a negation. It doesn't matter which one. That gave you what we did in dark blue, you see is right here. Everybody see that? And you got your books. It's there. Not quite as pretty as ours, but close. Okay? And by the way, every one of these examples has a checkpoint, and every one of the checkpoints you can get audio-video solutions for those checkpoints at larsonprecalculus.com. So please, soon as you can after class is over with, try to work the checkpoints at least, and if you can't get them to figure out, then go to the website and see if you can get help with that. All right. So those were our rigid transformations, shifts, horizontally and vertically, and reflections. The shape of the function didn't change. Now we're going to move to non-rigid transformations in which the shape does change. And these are basically stretches and shrinks. And that doesn't mean psychology. Oh, no, we wouldn't say that. Okay. So the horizontal shifts, vertical shifts, and reflections are all rigid transformations because the basic shape of the graph doesn't change. Those transformations change only the position of the graph on the coordinate plane, but the basic shape stays the same. It may turn over, shift, whatever. The non-rigid transformation of those that cause a distortion or a change of shape in the original graph. Now, it's not a major distortion, but it's a little bit. Okay? For instance, a non-rigid transformation of the graph, y is equal to f of x, non-rigid, is represented, here's one type. What you've done here, your g of x, is multiplied c, some number c, by f of x. Now give me a value for c, make up one. Second? 4, okay? Now, if you can imagine what f of x was, what do you want it to look like? A parabola, a cubic function, what? Just name something. One of those quartic functions, whatever, name something. Parabola, those are the, I like them, okay? Okay, so the parabola is going to be like this, that's the parent function, okay? Now, if I multiply each of those values here by 4, at 0, 0 is going to stay 0, 0. But 1, 1 is going to be 1, 4. And negative 1, 1 will become negative 1, 4. Okay? So what have you done? Stretched it upward. Okay? Slinky, or, those little string men that you used to pull and they did like this and made the thing out of something done like that. So that is a transformation. It's called a vertical stretch when that c is greater than 1. You said 4, that made it greater than 1. But if that c was between 0 and 1, notice our c's are usually positive for now. Okay? Between 0 and 1, give me a value between 0 and 1. 0.5, exactly. Okay, let's think of our parabola over here, going up like this. And it was 0, 0. Half of that is going to be 0, 0. Okay? But if you go 0, 1, or, 1, 1, or negative 1, 1, they're only going to go up to 0.5. So now what you've done is shrunk vertically. That's called a vertical shrink. Okay? Because your c is less than 1. Greater than 0, but less than 1. Now, another non-rigid transformation is when you have your y is equal to f of x, that's your parent function, think of the parabola or whatever, is represented by h, which is f of c times x. Now, what are you multiplying your c by now? Up here, you're multiplying by f of x, which is, but what was your f of x always? In this course, I said, remember this. That's your y. So you're stretching vertically or shrinking vertically. This time you're multiplying the c by x. Okay? So that means you're going to have a horizontal either stretch or shrink. Now, which way do you think it might be going? C is greater than 1. It's going to be a. Remember, everything dealing with x is backwards. So a big C is going to be a shrink. a little c is going to be a stretch. A little x's are so weird, aren't they? Okay? So that's what you have for the transformation. Horizontal shrink when c is large, and horizontal stretch when c is small. Backwards from the y's, right? Always remember, whatever, if you're dealing with the x, it's going backwards. Okay? Backward direction with rigid transformations, and backward stretches or shrinks with the non-rigid transformation. Okay? All right, so here's example 4. Okay. Let's compare the graph of each function with the graph of f of x equal to absolute value of x. Okay, let's get back to our dark color. And you tell me how to graph absolute value of x. Give me a few points. We're going to be doing this one. 1. Okay, we'll go right. What will your y value be? 1. Okay, so that's going to be right here. Next. 3. What will your y value be? F value be? 3. So that's going to be right there. Okay? Give me another x. 6. Boy, he likes big numbers, doesn't he? Okay. All right, that's going to be basically something about right there, I think. Okay? Give me another x. All right, finally. What will that be? 0. Okay, 0, 0. Okay. Y'all are very positive people, I can tell that, but we need to have a few negatives in here. Negative 2. Okay, that'll be somewhere over here. And what will its value be? Say again? Anybody? The absolute value of negative 2. 2! You got it. Okay, so it would be right here. Okay, somewhere there. Okay. Another one? Negative 4. Yeah, big number person. Okay. What would that value be? 4, right about there. Okay. Get a general idea what's happening here? Okay. That's going to be coming down like this or going up like that. Okay. V shape. That's your absolute value function. Okay. Now, what color you want H to be? Green? Is that what I heard? Okay, really? Okay. Light or dark? Light green. Okay. So the H of X is going to be your P green here. Okay. What will you be doing here? How does that relate to your F function that we've got graphed? For every X that you put in, you calculate the Y, and then you multiply by 3. So what's your Y value here? 0 times 3 is 0. What was your Y value here? Okay, it was 1. It goes up to 3. Okay, your Y value here was 2. Multiply by 3, you're up here to 6, wherever that is, somewhere about like there, right? And this was 3 here, 9. I think we're off scale. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. Maybe we can get that one in somewhere here. Okay? And here was a negative 4. That's going to be 4 times 3 is 12, somewhere way up there. So basically, it's going to be like this. What is that? A vertical stretch. You multiplied the Y by 3. Vertical stretch. Okay? All right, let's do the B part. What color you want the B part to be? Say again?
I said purple.
Purple. All right. Okay, the color of kings. Okay? The royal color. Okay. What in the world will that be doing?
Shrinking.
Say again?
Shrink. Go down.
Yes, down, yeah, okay. This way, yeah, okay, down, okay. So your values, 1/3 of 0 is 0, 1/3 of 1 is 1/3, 1/3 of 3 would be 1, 1/3 of 6 would be 2, 1/3 of 2 would be 2/3, 1/3 of 4 would be 4/3, just over 1, something like that. You see the general idea? Okay. The elephant sat on it. No, I'm sorry, it shrunk, a vertical shrink. Okay? And the same graph that you had here is just shrunk vertically by 1/3. This one was stretched vertically by 3. Does that make sense? Okay. All right. It shouldn't be talking about elephants in math class, should we? Okay, never mind. All right, so that's example 4. Let's erase what I've done. You'll be thankful for that. And let's see what they do. Here's your parent function, your absolute value of x function. 1, 1, 2, 2, 3, 3, 4, 4, 4, negative 1, 1, negative 2, 2, negative 3, 3, on like that. This is, by the way, let me just say it. The absolute value function is a piecewise defined function. It's minus x for all x is less than 0, positive x for all x is greater than 0. So you write it that way. They didn't, so I didn't, but that's what it is. By your first part, the A part here, they're multiplying every y value, that was your original y, by 3. So 0 times 3 is 0, 1 times 3 is 3, negative 1 times 3 here would be 3, 2 would be 6, negative 2 here would be 6. So there is your stretch function. Let's see what the shrunk function looks like. You're multiplying all the values by 1/3. 1/3 of 0 is 0. 1/3 of 1 is 1/3. 1/3 of this one is 1/3. There was 1. You're multiplying the y values. Okay, that would be 1/3. This would be a 2. Multiply that, you get 2/3. This was a 2. Multiply that by 1/3, you get 2/3. There it is, a vertical shrink. Okay. Oh man, that finished the section, but we didn't finish. They didn't do example 5, so we will start with example 5 next time. We'll wind up the section. Okay, let me give you some homework examples to do. You have all your check yourself checkpoints or whatever. So we'll do any of the odds 5, either 5 or 7 or both. Do number 9 that has multiple parts to it. Do number 11 or 13 or both. Then do any of the odds 15 to 19. All your odds are at calcchat.com. 15 is also at calcview.com. Okay, then do any of the odds 21 to 37. All those odds are at calcchat. Only 21's at calcview. Do any of the odds 39 to 45. All those odds are at calcchat, but 39's at calcview. Then do 47 and or 49. Both are at calcchat. And then 51, any of the odds 51 to 55. They're at calcchat. None of those are at calcview. And try to do 57 and or 59. Okay? I guess we'll wait on the others. There's just a couple more that you could do. We'll talk about those next time. Okay, before you leave home, I'm going to have to see if I can dig around and find you some graph paper. I have some in here, but as I was telling those who were here earlier, the copy machine was dead yesterday. I thought I just couldn't operate it, but I found out it wasn't just me, it was dead. So the things I left to be copied didn't show up. They weren't there this morning, so I had to try to make my own copies. It was still dead, so I couldn't do that. So here's a few pages. If I need more, I'll come back and dig around for more. If you've got graph paper of your own that you don't mind using, that's fine, but if you don't, I'll be glad to do it. Okay. Need graph paper? You don't? Okay. Need graph paper? Need graph paper? Okay. Need graph paper? You don't get anything. Need graph paper? Need graph paper? I'm sorry. Graph paper? There's only one draft. You graph paper? I'll do it. Okay. You graph paper? You graph paper? You graph paper? Got it? You graph paper? One day left.
She's Thursday.
No, you have a week to do it.
Okay.
Okay? That gives you the opportunity to ask questions on Thursday. Now, about that, here's a question I will not answer. Can you do number 7? Well, yes, I can, but I'm not going to because it's a quiz. But find anything like it in the book, I'll do whatever's in the book, and hopefully that'll get it. Now, if you say, what are you meaning by this? Yeah, I'll try to amplify, but if it's just how to do it, find something in the book like that.
Okay.